Swayam Prabha. Digital India. Educated India.
So that's what I was saying, that this result is very powerful because it really gives an easy check. Yeah, if I have k vector fields in the distribution, I just have to check their combinations. Yeah, so kc2 and you are done. Okay, check that their combinations belong to the distribution and you are good to go. Okay, proof. Of course, whenever we do something, we have to prove. It's an if and only if, so you have to prove both sides. First, suppose if you have involutivity. If you have involutivity, then this is obvious, right? Because involutivity means that if f1 to fk belong to delta, then their Lie brackets have to be in delta. So this is obvious by that if you are starting with involutivity, obviously this will happen, no problem. The bigger question is, if you start with this, that only their combinations are in delta, then can you claim that the distribution is involutive as per this definition? Okay. How do we go about it? We take some two vector fields, okay, g1 and g2 in delta. Okay. Now the important thing is, because g1 and g2 are in delta, and that happens at all points, you should be able to write them as a linear combination of the fi's. That's the only way g1 and g2 can belong to delta, right? Because they have to be the linear combination of the fi's, right? And of course, these phi ij's are smooth functions. Yeah, smoothness is coming out of the fact that fi fj's are also smooth. Yeah, and g1 g2 are also smooth. Okay, therefore this coefficients have to be smooth. Okay, so it's everything is smooth, so the coefficients also have to be smooth. Okay. For simplicity, if you assume k equal to 2, that is, you have only two vector fields here, f1 and f2, forming the distribution, just so that the proof looks easy. Yeah. Then what do you have? You have that the Lie bracket of g1 g2 is actually this guy, Lie bracket of this, right? Because I have written g1 as phi 1 1 f1 plus phi 1 2 f2. And g2 as phi 2 1 f1 plus phi 2 2 f2, right? Because g1 g2 belong to the distribution, right? Now I want to compute this Lie bracket. Okay. Now there is a problem with this computation. Okay. So I want you to actually, this is another exercise. I need you to complete this computation. This computation is pretty straightforward. It is just doing this. With some coefficients, phi 1i fi plus phi 2j fj. Remember, phi 1i and phi 2j are depending on x, and they're just they're functions. They're not just constants or anything. Okay, all right. So I wanted to prove this computation anyway, but let's look at the Lie bracket of g1 and g2 as per this expression. Okay, it is known that the Lie brackets are distributive. I have not talked about this. Yeah. But it's easy to prove that they distribute. That is, I can break this open. How? In all these four terms. Yeah, just works like a nice distributive bracket term. Okay. So from g1 g2 I will get phi 1 1, phi 2 1, f1 f1 first term. Then I will get phi 1 1, phi 2 2, f1 f2 second, phi 1 2, phi 2 1, f2 f1, and phi 1 2, phi 2 2, f2 f2. Now it should be obvious to you that the Lie bracket of a vector field with itself is 0. Just 0. Okay. So these two are gone. Okay. These two are gone. So what am I left with? I am left with these two. Okay. And these are actually the same term, I can actually flip the sign. So also this is another thing that's true, Lie bracket is antisymmetric. So F1 F2 Lie bracket is negative of F2 F1 Lie bracket. Yeah. So I can flip the sign. So what am I left with? I am left with something rather simple, right? It's yeah, this is my G1 G2. Okay. Okay. Now what have I assumed? That F1 F2 belongs to delta. Yes. Yes. Which means what? G1 G2 also belongs to delta. Why? Because it is just a scalar multiple of F1 F2. Yeah? No? What do I have to prove for involutivity? Take arbitrary two vectors, vector fields in the distribution and prove that their Lie bracket is in the distribution. Yes? What does it mean to be in the distribution? They are linear combinations of the forming vector fields. Okay? I have assumed that there are only two vector fields, forming vector fields, yeah, or generator vector fields, which is F1 and F2. So G1 and G2, if they are in delta, means G1 can be written as phi 11 F1 plus phi 12 F2, and G2 can be written as phi 21 F1 and phi 22 F2. Notice phi 1, phi 11, phi 12, phi 21, phi 22 are functions of x, but scalars. They are not changing the vector direction. This is in the direction of F1. This is in the direction of F2. It's like multiplying a scalar and a vector. And just that here, it's not just scalars, it is a scalar function. Similarly, it's not just vectors, it is a vector field. That's it. Okay. So, phi 11 F1 is in the direction of F1, phi 12 F2 is in the direction of F2. Similarly, phi 21 F1 is in the direction of F1 and phi 22 F2 is in the direction of F2. Okay. The important thing to remember about Lie bracket is that they distribute nicely. That's what I have used. I have just broken open the bracket just like you would break open any product. Works exactly like this. Yeah. So I get 4 terms. Now out of these 2 terms have same, F1 comma F1 and F2 comma F2. Okay. Just because the Lie bracket is antisymmetric, this structure, this is 0. If G and F are the same, this is actually the 0. Then becomes a 0 vector field. So this guy is 0, this guy is 0. I am left with F1 F2 and F2 F1. And so that is negative. So F1 F2 is negative of F2 F1 again by antisymmetry. So all I have left is this entire guy. Okay. And this is just a scalar. Yeah, fine, scalar function, but still a scalar, not changing the direction of the vector. Yeah, and I have already assumed that F1 F2 belongs to the distribution. So I am done. G1 G2 belongs to the distribution now. Now if I had assumed instead of 2 F's, there were many more K generating F's, yeah, or say 3, what would happen? I will get 3, phi 11, phi 12, phi 13, phi 21, phi 22, phi 33, but I will still get combinations of these and repetitions, repetitions, and the combinations are already assumed to be in the distribution, repetitions are dying, so therefore I will always remain in that. Okay, so straightforward actually, yeah, you don't have to worry too much. Yes, good point. I was also wondering. One should always ask oneself, are we using all the assumptions? A non-singular distribution, if delta is a non-singular distribution, then involutivity if and only if. Okay. You know what? So what you are asking is that where do we use the non-singularity of the distribution? All right. Now, this is where I think the problem will happen. This place. I think this equality is no longer writable. is what I am wondering, or am I wrong? I think this equality is where I will start having trouble. Yeah, I have to think about it more carefully, but I believe this equality you will not be able to write anymore. Because if your distribution is changing rank, the span is changing rank. Now the span definitely has to hold the vector, because we are assuming that gi is in delta. So obviously the span has to hold the vector, but my feeling is you will not be able to do it with smooth functions here. Yeah, if you suddenly want to jump from one point P to another point P prime, you go from a 3-dimensional distribution to a 2-dimensional distribution, alright, because it is singular, then this phi will undergo a rather drastic change. I do not think you will be able to retain smooth phis anymore. Again, I have to think about this more carefully, but this is where I think things will go wrong. This assignment will not lead to smooth functions phi. But that's a good point. I'll try to hunt it up. Huh? That's also the next question I was asking myself. Alright. Where are we using the smoothness of the functions phi? See, when I look at this, without a smooth phi, this is poorly defined. Fine, I wrote this as this split and all this, alright. But if I try to actually compute this guy by this formula, you can see I am starting to take partials of the phis. And here. So this is poorly defined. So even writing like this is not okay. Because I mean eventually all the bracket operations are, these are all derivatives of some kind or the other. So I am frequently taking derivatives. Yeah. So I will definitely mess up. I mean this is not a good, I mean not a well defined object anymore. Yeah. So it almost certainly, I believe what I am saying is right, that non-singularity will result in these phis becoming non-smooth. Because you can't just jump rank and expect that everything will turn out to remain smooth. This will definitely create some trouble. You are suddenly projecting to a plane. Say you are in 3 dimensions, suddenly you are projecting to a plane. Yeah. Or in 5 dimensions to a 4-dimensional hyperplane or a 3-dimensional hyperplane. That will not retain good values of the phi. I mean, yeah, I mean as of now whatever I am saying is imagination. It's nicer to if we can construct and sort of evaluate. Yeah, but I believe that's what will go wrong. Okay, I'll check anyway if I can find some fun examples. Yeah, alright. So here I am just giving some example of this normal form business. Okay, this is again going back to the previous topic, but anyway let's look at this. Yeah, so this is sort of the system. Yeah, and I want to put this in normal form. You can see it's already nonlinear and messy. I am using y as x2. Alright, I am using y output as x2. I want to get this to normal form. How do I do this? I simply start taking derivatives, right? First to get the relative degree, right? Because anyway the y and its derivatives become my states, my linear states, right? So the first state is x2 itself, then I take a derivative and I get to x2 dot, which is x3, right? And then I take another derivative y double dot, which is x3 dot, which gives me the control. Okay, so this is a relative degree what system? What's the relative degree of this system? 2. Yeah, it's 2. I have also written it here. Yeah, I took 2 derivatives of the output. Whatever output I was given, I took 2 derivatives, I reached the control. So obviously my first 2 states become this guy. Yeah, that is y and its derivative. Those become my first 2 states or the last 2 states. Then I need to find the phi state. right, which will make it a diffeomorphism. Suppose I choose this guy x1. This is a problem because the derivative of x1 contains the control, so I don't like it so much because it's not going to give me the normal form. Now what do I need for the normal form? If you remember, I need I've actually written it here. I need LG phi equal to 0, right, so that there is no control term appearing. So right. So what is LG phi? LG phi is basically partial of phi with multiplied by G. What is G? G is basically whatever is multiplying the control, right. So that's 2 plus x3, 1 plus x3 whatever, 2 plus x3 square, 1 plus x3 square, 0 and 1, this guy. So if I compute this product, I get this. I can actually break this open to get 1 plus x3 square this, del phi del x1, del phi del x3. Okay. Now I want this to be 0. Okay, and I want to use this to motivate my new state. Okay. So I have of course chosen it like this. Yeah, pretty scary looking actually. How do you think I came with this? So this is my phi, right? This is what I chose as phi. How do you think I came up with this? I did some guesswork. Alright. So if you look at this guy, yeah, this looks like tan inverse derivative of tan inverse x3, right? This looks like derivative of tan inverse x3. So if I keep x1 as linear, right, I get del phi del x1 as 1, right, and then I get del phi del x3 as 1 over 1 plus x3 squared, yeah, 1 over 1 plus x3 squared, and then this guy is again just multiplying del phi del x1, which is 1, so these two will cancel out and I am left with, I apologize, did I get this right? Yeah, and this and part of this will cancel out. This is basically del phi del x3 is going to give me minus 1 over 1 plus x3 squared. Okay. So I did a little bit of guesswork. How would you do it if I wanted to guess a phi starting from this equation? Is there any other smarter way? I thought it just bunch of guesswork. I just looked at what I can cancel. Is there any nicer way that you can think of to sort of arrive at this? No? Because individually I can't say that individually these are 0 or something like that. It's not a quadratic or anything. So I can't say that individually these are 0 or some such, right. One thing that's obvious to me is that I don't have this entire equation has only x1 and x3. So I don't need the phi to depend on x2. That much is obvious to me. My phi doesn't have to depend on x2 because it is playing no role in this entire equation, right. So phi is only a function of x1 and x3 is all I know. Yeah, I think to me it seems this is what works fine. Okay. And anyway, if I choose this funny looking coordinate, I get z1 dot as this, z2 dot as z3 and z3 dot as this, z1 z3 plus u. Yeah. Oh no, it won't work. X1 minus tan inverse x3, is it? So del phi del x1 will be 1 and del phi del x3 will be minus 1 over 1 plus x3 squared. So this will be 1 over 1 plus x3 squared and this will be 1 over 1 plus x3 squared. So 1 remains, no? So I am trying to cancel the 1 also. That's why I put the minus x3 here. I must have tried with that only, but then I added the minus x3 because I have to cancel the 1 also. Okay, that's it. Yeah, it's just a little bit of hit and trial. Okay, but this is what you get as the dynamics. You still get nice enough zero dynamics, by the way, if you see. Yeah, because if the linear part goes to 0, this guy is 0 and this is again an exponentially stable system. Okay. So again, started with something complicated and very non-linear, not evident how I would design a control based on any methods that I know, yeah, but I still end up with something rather nice. Okay. Ooh, this one I guess it's already in your notes. Why is this exercise then? Oh, I see. Apparently it's not exercise. I've already solved it, so it's already in your notes that I uploaded. So I should probably just not say this is an exercise. Solved. Yeah, because you can see that it's here. I mean, I've actually done it. Anyway, you can take a look at this. Yeah, you can take a look at this in your leisure time. This, whatever expression you get here. Yeah, I believe this expression has a problem. This expression has a problem. So anyway, so I got to this expression. I'm not sure why I'm saying this is specialized to k equal to 2. Doesn't seem like this is k equal to 2 is necessary here. Yeah, it seems it's specialized to k equal to 2. Yeah, because otherwise there would be summations and stuff. That's all. Alright. Okay. Anyway, this is something you can just look at it on your own. Alright. So anyway, next time we'll continue with our discussion on Frobenius theorem. Alright. Okay. Alright. We'll stop there. Thank you.